exponents today, properties of exponential functions, I should say. And so we're going to forge right on ahead. And for those of you that are in Puerto Rico, we pray for you, we love you, we miss you. Be glad when you come back and you can tell us all the stories about what God did while you're there. But right now we're going to look at these exponential functions. We started looking at them before the Easter break just a little bit. And as we know, every one of the types of graphs that we've had so far has had a way to move it left or right, up or down, and stretch or compress, or reflect, turn around. So we need to take a look at what that looks like in an exponential function. So we already looked at how to graph this exponential function. If we did a chart of values, if we had 2 to the 0 power, that would equal 1, so that's why the ordered pair 0, 1. If we had 2 to the first power, that would give you 2. That's where the ordered pair 1, 2 comes from. And so on and so forth. If you plugged in the values, you would get these. So this is a parent function of an exponential growth function where we've got 2 is our base and x is our exponent. So the parent functions obviously would look a little bit different depending on what your base is. But here's your exponent. But this parent function can get moved around if you alter the exponent or if you alter what is added or subtracted from the whole thing, or if you multiply this growth part by a whole number, okay, or by a fraction. They can all make a difference. So for example, let's take a look at this function right here. Now there's a couple of things happening here. First of all, this number out front has a negative in front of it. It's also a fraction. So from your knowledge and from this that we just looked at, is this going to affect our left and right? No. Is it going to affect our up and down? No. What's it going to affect? Stretch or compress. So from your knowledge from before, is it a stretch or a compress? It's a compress. It's going to shrink it down by a half. And what's this negative going to do to it? Upside down, sure. So it's going to flip it over and it's going to cut all the values in half. So what you can do is, the easiest thing to do would be point by point, is cut the values in half and then jump it over the x-axis. So this number is on 1. How much is half of 1? A half. And then we'll flip it over to the other side of the axis. Okay, so we have, here's 1. Half of 1 is half. But the negative flips it to the other side, so it would put it down here. How much? This one is at what? It's at 1. What's the ordered pair? What's the y value here? 2. So it's at 2. How much is half of 2? 1. And then flip it to the other side. This one is at the ordered pair 2, 1, 2, 3, 4. Okay, it's at 4. How much is half of 4? 2. And then flip it to the other side. So really for every one of the points, you're taking half of it because of the half, and the negative flips it to the other side. So we end up having it flipped over, and it's compressed. It's not quite as steep as the original one, because each one is half. Like this one was 4, it's now 2. This one was 6, it's now 3. So it's got a more gentler type of a curve because it's only half as big rather than regular size. And so if you multiplied it by a number that was bigger than a half, it would get steeper. Hopefully that makes sense. Okay, so that's what happens when you've got a thing in the stretch or the compress place with a certain function. we need to then take a look at, well, what about some of those other locations? What about when you have a number right here? That should be on your sheet to fill in. Okay, so we're ready. Okay. What is happening? The x minus 4 tells us something, and the 3 tells us something. What does the x minus 4 tell us? It tells you right or left. From your knowledge from before, is it going to be right or left? It's going to be to the right. Remember, it's x minus h. So this would tell us that we go right 4. So you can write 4. And we know that there's an issue with the writing on this particular tool. What's the 3 tell us? It's a stretch of 3. So you would write out the word stretch of 3, moving right 4. So what we do is we can go point by point, multiplying by 3, and then moving to the right 4. So this value is 1. 1 times 3 is 3. So we go up to 3 and then move it right 4. 1, 2, 3, 4. Dot. So 1 times 3 is 3, and then right 4. 2 times 3 is 6. So 1, 2, 3, 4, 5, 6, and then move it right 4. 1, 2, 3, 4. Oops, I missed. Okay, so on like that. Now, because we're not really quite, that's the next one would be like super high. We're going to just take a look at here. What about here? This would be the point 1/2. It's -1 goes with 1/2. So how much is 3 times 1/2? 3 times 1.5. So we would go up to 1.5 and then move right 4. 1, 2, 3, 4. And then what would happen is we would put in our line here, and it stretched it out a little bit. It still will eventually go down. It still will eventually go down, but here's what we had done is, so 4 times 3 would give us 12 plus 4. That one we didn't do. 2 times 3, I don't have this one in. 2 times 3 was 6. And then move it over 4 would have given you here. Okay, that's the one that I didn't put in. So it's actually there. And then on so that it makes that very nice shape like that. So times 3 and then right. So if you do that in that order, whatever this is first, and then move the right or left, you're going to have a very nice representation of the curve from the parent. And we're not doing a super big ton of these. I do need to get us to the point where we can get to a special formula that is used in economics. But you're going to be doing these for practice in the homework assignment, as you know, and go through. I do want you to use graph paper. I've got graph paper so that you can, get a few points on there and get them moved around and do a really good job with it. All right, our next one. If you turn the page over. Okay, this one. Is there a stretch or compress on this one? No. Is there a right or left on this one? So what is there? There's an up and down. So what is this, up or down? Down. Down 3. Because this is our k value. H is the one that would be attached to the x, and k is this one. So it goes down 3. So this one's the easiest one by far. All we have to do is count down 3 for all the points. 1, 2, 3. 1, 2, 3. And then 1, 2, 3. We like this one because it's easy. It's not stretched or compressed. However, the one thing that did happen, guys, okay, notice that we have a line here that it didn't cross. It gets closer and closer and closer to 0 in the original one. But when you have a scenario where it moves the whole thing down, that asymptote, in other words, the number that it approaches, also moves down. So really, really important that when you draw this curve, it does not go below x equals negative 3, okay? It goes right down to it, but it does not go below x equals negative 3. And I believe I have that written in there for you. This is actually the graph, okay? Easier to draw because you just go down 3. The only thing you have to really watch out for is that you do not go past, if you were to do this on a test or quiz, and you dipped this down below the negative 3 mark because you've got the basic pattern going, you would get something taken off for that because this dividing line from what values you would get is just shifted down to negative 3. Because these values are still approaching 0, approaching 0, approaching 0 from what we had looked at before, and then the whole thing just plumps down to there so that it's approaching negative 3 like that. Okay. Now, in the interest of being able to get to what we also need to get to, if we were to take this concept and we were to work with it and work with it, what we would find is that asymptote, okay, that bottom line, okay, that base line, okay, if we had this crazy formula right here, y equals 1 plus 1 over x to the x power, you would find that it bottoms out at a number called the natural base, okay, and this e, okay, it is called E. It's a very special number. It's kind of like pi is a very special number, and I is a very special number, being square root of negative 1. E is this very special number, 2.71828. It goes on and on and on. But a man named Leonard Euler, E-U-L-E-R, actually developed this and a lot of the symbols that you see in algebra. And so E kind of stands for Euler, but it's also the natural base, and it's important in this formula. Now, something really awesome about Euler is Euler was a very humble man, okay, and he was also a very strong Christian. Okay, he was famous for not demanding credit for things he discovered, and he was probably arguably, but not too arguably, he was one of the greatest mathematicians that ever lived. You don't hear as much about him because the other guys were not as humble, okay? But a lot of the symbols, when we have the f of x notation and a lot of the other notations, Euler was responsible for setting those notations, making it so that it was accessible to more people, because if you have symbols to represent things, more people can understand them than normally could. He was also an amazing educator. I'm reading right now letters that he wrote. It's called Euler's Letters to a German Princess, because Frederick the Great had a niece, I believe, and he wanted her to be educated. And so Euler wrote these letters to explain math and science to her, and it was eventually even used as a textbook, these letters that he wrote to the German princess. So they are collected in 2 volumes. I bought them recently. I'm working my way through them. They're very, very good. Every so often he throws, because his life was also dedicated to God. When he's writing, he links it in with God very, very well. And so he's a great example of someone who's a brilliant mathematician, as well as being a good, strong Christian. He would pray with his family, gather them together, so that they could have devotions every night all through his life. He had a reputation for being a really nice guy. He finished well. He finished his life as a grandfather, actually passed away with, basically he was in his den, just spending time with his granddaughter and just went off into eternity. And it's just a very sweet thing. Yes, he had kids. He had a granddaughter. He had many children. Unfortunately, because it was the 1700s, I believe only 5 of them survived to adulthood, but he had, I believe, 13. So okay. Anyway, this formula. Okay, here we go. The formula. The continuous compounding formula. If you'll notice, it still is an amount. Okay, we had a compounding formula, guys, that dealt with compounding something on a yearly basis or in one increment at a time. This constant E, that natural base, if we apply it in this formula, principal equals E to the RT, where R is rate and T is time, P is principal, then you can get a new value and you get a little bit more interest if your bank is continuously compounding as opposed to if they are incrementally compounding. So as you look into investments, you might want to consider that. Because if we have a problem, and this is on your sheet, you invested $1,000 in savings account 6 years ago. This is the same problem we did in section 1. The account pays 5% annual interest, and it's compounded continuously. How much do you have now? What we do, P stands for principal. Principal is $1,000. R is the rate. But we need to make that into a decimal. What is the rate as a decimal? Good. 0.05. Move the decimal over 2. And the time, how long is it invested for? 6 years. So what we do is we plug it into that formula. And we can put this in our calculator so that we know. I want you to see where the E lives in your calculator. So we're taking 1,000, yes, times E is the second button of the divided by sign, second E. Caret means to the power of rate 0.05 times 6. Oops, I've got 2 times in there. That'll make a problem. Delete. There we go.
You can do that.
And then we can hit enter. So there you go. So now you know. So we get $1,349.86 by doing that process. Second. And so compounded annually, if we remember from when we did this in this first section, we got $1,340.10. You don't have to turn there. Just believe me, we did this one in the other section. And compounding continuously over 6 years gives you just a little bit more interest. Now, this may not seem very much on a $1,000 investment. However, on this one, on a bigger investment, that you would have that. Okay, all right, so well, you could do the calculation and figure that out, Mika. That would be a great idea. Okay. All right, so we're going to close this down for now and let you get some time to work on your assignment. Tomorrow's lesson is also not going to take the whole period. I spent a lot of time on the history of Euler today, which is good because he's awesome. Look up stuff about Euler. Good.